On March 16, 2026, something goes down that flat out should not be happening. By pure chance, an interstellar object known as 3I/Atlas, something that came from deep space outside our solar system, slides past Jupiter in a way that makes scientists stop breathing for a second. Not just a casual flyby, not a wide miss, but a pass so exact it lines up almost perfectly with one of the most sensitive gravitational boundaries we know about. That alone raises eyebrows. But once you start breaking down the numbers, the physics, and the timing, things turn uncomfortable real fast. This is not how random comets move, and it's definitely not how uncontrolled space debris behaves. 3. I/Atlas is not drifting aimlessly. It's not wandering lost through the sun's backyard. It's not whipping around in some sloppy slingshot motion. Its trajectory locks onto a gravitational target so insanely precise that the odds of hitting it by accident are worse than getting struck by lightning twice in one lifetime. And the closer scientists dig, the harder it becomes to call this coincidence. Because that path doesn't look random anymore. It looks deliberate. To really grasp why this matters, you have to forget the watered-down gravity lessons from school. This is the real deal, the version mission planners and astrophysicists actually use. Every planet controls a hidden region of space where its gravity temporarily overpowers the sun, and inside that zone, everything changes. That region is called a Hill sphere. Inside this invisible boundary, the planet becomes the boss. Objects entering it start behaving differently. Paths bend sharply, speeds shift. Capture becomes possible. Jupiter's Hill sphere is the biggest heavyweight in the solar system, massive enough to hold dozens of moons and act like a cosmic staging area. Engineers aim for this zone on purpose. Inside it, fuel costs drop hard. Tiny course corrections suddenly pack real punch. Gravity does the heavy lifting for you. This isn't just useful, it's the most powerful gravitational gateway we've got. Now here's where things stop being normal. On March 16, 2026, Jupiter's Hill sphere measures roughly 53,502 million kilometers in radius. Independent orbital models using data pulled from over 200 observatories all point to the same thing. 3. I/Atlas is expected to pass Jupiter at a minimum distance of about 53.4145 million kilometers. Those numbers are almost identical. The difference sits comfortably inside observational error. That's not close by space standards. That's surgical precision. That puts Atlas right on the razor's edge of Jupiter's gravitational gate, the exact zone where capture, deceleration, or orbital manipulation becomes possible. Random objects do not thread needles like this, not without reason. And that's why this flyby has scientists quietly asking questions nobody wants to say out loud yet. This situation turns physically possible and way more unsettling once you factor in one brutal truth. Atlas shouldn't even be there, not naturally, not by accident. Interstellar objects rip through solar systems at insane speeds, and Atlas is no different, clocking roughly 65.9 kilometers per second as it tears through space. At that velocity, Jupiter shouldn't mean a thing to it. A normal comet would blast through the system and keep it moving on a clean escape path. No slowing down, no hanging around, no careful lining things up like it's following instructions. But here's where gravity flips the script. Inside Jupiter's Hill sphere, the escape velocity drops to about 2.2 kilometers per second. That gap is massive. It means that a tiny nudge, almost nothing by space standards, could suddenly allow an object to linger near Jupiter instead of flying past. Moves that are flat out impossible outside the sphere suddenly become doable inside it. This is exactly why spacecraft engineers love this region so much, and this is where the story takes a sharp left turn. When 3I/Atlas passed perihelion, its closest point to the Sun, astronomers spotted something wild. A sudden burst of non-gravitational acceleration. Not slow, not smooth, A quick, sharp push that changed its path just enough to line it up almost perfectly with Jupiter's Hill sphere. That adjustment was tiny, roughly 1/10 of a million kilometers in cosmic terms. But that microscopic correction is the only reason Atlas hit this alignment months later. Without it, the object would have missed Jupiter's gravitational gate completely. Harvard astrophysicist Avi Loeb ran the numbers, and they're ugly. The odds of this happening by pure chance? 1 in 26,000. That's not guesswork. That's based on orbital mechanics, known forces, and real error margins. And that number only works if Atlas behaves like a normal comet. But Atlas doesn't play by normal rules, and the timing makes it even more uncomfortable. That sudden acceleration happened while Atlas was hidden behind the sun. Earth-based telescopes couldn't see a thing. No direct imaging. No real-time confirmation. If someone wanted to adjust a trajectory quietly, without eyes watching, that moment is exactly how you do it. Once Atlas finally slipped out of the sun's blinding glare, astronomers started catching details that didn't sit right at all. What they saw weren't messy, random bursts like you'd expect from a natural comet. Instead, Atlas was throwing off focused jets of material, tight, controlled, and stable, popping off at moments that lined up perfectly with changes in speed. That's not normal behavior. Natural comets burp gas in all directions as ice heats up and breaks down. Atlas didn't do that. Its activity looked organized, timed, and directional, like something was managing the release instead of letting chaos run wild. Then came the structural red flags. Measurements hinted at a core far denser than what interstellar comets usually carry. Not soft, not fragile. This thing was tough. Atlas survived brutal solar conditions that have shredded other comets way farther out. It powered through intense solar storms, including a massive coronal mass ejection in November that should have torn a loosely held icy body to pieces. But Atlas stayed intact. The chemistry only made things stranger. Tests showed unusually high nickel levels with very low iron. In nature, nickel and iron are born together in stellar explosions. You don't get one without the other. Yet Atlas showed a ratio closer to what you'd see in engineered alloys than random cosmic leftovers. That doesn't prove anything by itself, but it definitely adds weight. Then look at the route Atlas took through the inner solar system, clean, efficient. It passed near multiple planets without drifting into chaotic zones. It stayed hidden during key moments and lined up with Jupiter's gravitational gate with precision measured down to 1 part per thousand. Natural systems are loud, messy, wild. This wasn't. Even the small stuff started stacking up. Rapid brightness flickers, strange polarization in reflected light, focused jets instead of diffuse gas clouds, low water content compared to other long-distance objects. And it came from a stretch of sky already tied to unexplained signals in the past. Any one of these could be brushed off. Together, they start looking like a pattern. Scientists tried grounding the acceleration in solar activity, and to be fair, the sun was acting up. Atlas flew through heavy eruptions, including powerful X-class flares. Plasma pressure and extreme heat could, in theory, disturb gas flow and create uneven thrust. But theory and clean execution don't always line up, and Atlas keeps skating that line a little too perfectly. That explanation starts falling apart under pressure because just weeks later, Atlas ran straight into an even bigger solar outburst. A massive coronal mass ejection stretching over 1 million kilometers, on par with some of the most violent solar events ever recorded. Events like that have wiped comets out completely. Atlas didn't flinch, it stayed intact. That kind of resilience becomes another red flag. Some researchers tried brushing it off, saying Atlas's route near the solar equator just happened to expose it to repeated flares. Others argued that even with perfect geometry, the resulting trajectory still demands an insane level of coincidence. And coincidence starts sounding weak when the same unlikely outcomes keep repeating. Here's where ignoring this becomes impossible. Jupiter's Hill sphere isn't just a cool gravity trick. It's the best location in the solar system to slow objects down, deploy probes, and establish long-term presence using minimal energy. If you were planning a reconnaissance mission into a foreign solar system, Jupiter would be the obvious anchor point. Massive gravity, stable orbits, natural shielding, built-in concealment, and Atlas is heading straight there. This does not prove that 3I/Atlas is artificial. Science demands restraint, but it also demands honesty. And honest analysis shows Atlas behaves nothing like any natural interstellar object we've ever studied. Its path is too precise, its adjustments are too perfectly timed, its structure is too durable, its chemistry is too strange, and its destination is way too useful. Whether Atlas turns out to be a rare natural anomaly or something else entirely, one thing is locked in. This object is forcing scientists to stare down some deeply uncomfortable possibilities. Not all interstellar visitors are just random debris. Some paths may be shaped, some arrivals may be intentional, and not every mystery crashes in loudly. Some arrive quietly, they correct course behind the sun, and slip perfectly into a gravitational gate millions of kilometers wide. On March 16, 2026, all eyes will be on Jupiter. Because whatever happens next, 3I/Atlas is no longer just passing through. Drop your thoughts in the comments, smash that like button, subscribe to the StellarDrift channel, share this video, and I'll see you on the next one.